Okay, let's take a look at this problem. When you set this up, we were given information about the number of moles and the volume of the flask. So we have to divide 0.2 moles of phosphorus trichloride by 5 liters, and we get 0.040 molar. And the 0.1 mole of chlorine in 5-liter flask, we get 0.020 molar. We're also told, as I've written here on the bottom, that we get 0.012 molar PCl5 at the end. So now we can fill in our chart. We know that we start with 0 product to begin with, so the change is a positive 0.012 molar. Looking at this one, we have 1-to-1-to-1 stoichiometry. Because it's all 1-to-1, if the PCl5 goes up by 0.012, each of these reactants has to go down by 0.012. And I know some people got the wrong idea from the previous example that these two numbers had to add up and equal the change in the products, and that is not what was going on. It was just coincidental that they did because the previous problem was 1-1-2 stoichiometry. So now when we subtract, we get our equilibrium concentrations, 0.028 molar, 0.008 molar, 0.012 molar. So we set up our equilibrium expression. K sub C is equal to the PCl5 concentration divided by the PCl3 concentration times the chlorine. Plug in the numbers and the calculator says 54. But we only had 1 sig fig from subtraction here, so we have to report 50 as our K value. Now, the first two examples that we did, we looked at the ice chart and we put numbers in all along the ice chart. Sometimes we don't put numbers in, we need a variable. So instead of solving for the K value, we can actually go into tabulated data, look up the K value for well-known chemistries, and we can solve for the equilibrium concentrations. And that's going to be about 90% of what we're doing for the next 4 chapters, is solving for equilibrium concentrations. So let's look at an example. We have this carbon monoxide reacting with water gas to make carbon dioxide and hydrogen. The equation is balanced when we check. And we know that we have 4.06 is our K sub C. We have 0.1 moles of carbon monoxide and 0.1 moles of water placed in our reaction vessel. So that makes the math pretty easy to start. But the first thing we'll do is look at this and write our mass action expression or our equilibrium expression. So K sub C is equal to the product concentration, carbon dioxide, times the hydrogen concentration, divided by the carbon monoxide concentration times the water. And again, this is water gas, so it does get included. We don't put water in there when it's a liquid. Now we'll calculate the molar concentrations. We know that we have the carbon monoxide. We have 0.1 moles of water in 1 liter. That makes the math easy. I can do it in my head. So it's 0.1 molar. And we have the same concentration for the water. We have 0.1 moles per 1 liter, and that's equal to 0.1 molar. And again, it's coincidental that these are the same, and it's going to make the math easier. Later on, we'll talk about what happens when they're not the same and the math's not easier. So now we fill out our chart. 0.1 molar carbon monoxide, 0.1 molar water. That's all we know. We don't have any information about what happens later. So this is where we use a variable. How much carbon dioxide and hydrogen is in there before any chemistry is taken place? 0. So we can start there. Now we know that some of this is going to react and it's going to produce products, but we don't know how much. What do we do in algebra when we don't know what something is? X. So this will go down by X, some unknown amount. 1, 1, 1, 1 coefficients in the balanced equation. So these go down by X. These two products increase by X. So at equilibrium, I have 0.1 minus X for the two reactants, and I have X for my two products. So now I can set up my equation and solve. I know that my equilibrium constant Kc is equal to the carbon dioxide concentration times the hydrogen concentration divided by the carbon monoxide concentration times the water because it's a gas. So my Kc value is 4.06 is equal to carbon dioxide X times hydrogen X divided by carbon monoxide 0.1 minus X times the water concentration 0.1 minus X. So now 4.06 is equal to X squared divided by the quantity 0.1 minus X squared. Now, when we look at this, because I have two terms that are squared on the right-hand side, the easy way is to just take the square root of both sides to solve this. So the square root of 4.06 is equal to X divided by 0.1 minus X, and that's equal to 2.01. So now we can rearrange. 2.01 is equal to X divided by 0.1 minus X. So multiplying both sides by the quantity 0.1 minus X is equal to X. So I get 0.201 minus 2.01 times X is equal to X. Now adding the X to both sides, I get 0.201 is equal to X plus 2.01X. So 0.201 is equal to 3.01X. 0.201 divided by 3.01 is equal to X. And that is equal to 0.0668 molar. Now that's great, I found X. But this problem didn't say what's X. This problem said, what are the concentrations of all the reactants and products at equilibrium? So now I have to take X and go back up to my equilibrium line on my chart. I know what X is, 0.0668 molar. So at equilibrium, the carbon dioxide concentration and the hydrogen concentration are 0.0668 molar. At equilibrium, the carbon monoxide concentration and water concentration are 0.100 minus 0.0668 molar, so we get 0.033 molar by subtraction. And again, you need to watch your significant figures here. And we go out to the third decimal place, so we don't get to keep 3 sig figs in these two numbers, but we do keep the 3 sig figs here. So now, just out of curiosity, I want you to look at this algebraically. If these numbers had both not been 0.1, what would have happened algebraically? You'd have to FOIL, and what would FOIL give you? The middle term, and when you took all the terms and wrote them out in a nice equation, what kind of algebraic equation would it be? A quadratic. And I know you know the quadratic. I know you have solved the quadratic. I don't like them. We avoid them whenever possible. And we're going to talk about some simplifications we can make later on to avoid solving the quadratic. Sometimes there's no avoiding it, but we will generally avoid it. So now, go ahead and do the problem on the next page. Now, this one's a little bit different than mine because of 1, 1, 2 stoichiometry. So be mindful of that stoichiometry. Go ahead and do this with your groups.